Hey, Math 30-2s. Today we're going to look at polynomial functions degrees 0, 1, and 2. So a polynomial function consists of one or more terms which are separated by positive or negative signs. We already met polynomial functions in one variable in previous math courses. For example, the function f at x equals x squared minus 4x minus 5. That was a quadratic function. F at x equals 2x minus 4 is a linear function. F at x equals 3 is a constant function. It's also a line. The degree of a polynomial function is the value of the highest exponent in that function. If a polynomial function includes a term with no variable, this term is called our constant term. So a constant term has no variable. Let's review that. You learned that in grade 10. We'll complete the following. The degree of f at x equals x squared minus 4x minus 5 is 2. Highest degree is 2. And the constant term is the one without a variable, minus 5. The degree of f at x equals 2x minus 4. Well, x has a degree exponent of 1, so the degree is 1. The constant term is negative 4. And since f at x equals 3 can be written as 3 times x to the exponent 0, we say the degree of this thing is 0. A number that multiplies the variable in the polynomial is called the coefficient, and the leading coefficient is the number that multiplies the term with the highest power. That's our leading coefficient. So complete the following. The leading coefficient of this function is 1, 1x squared. The leading coefficient of the next function, 2x minus 4, is 2. In a polynomial function, all the coefficients must be real numbers, and all the exponents must be whole numbers. That's the definition of a polynomial function. So write a polynomial function that satisfies the following conditions. Degree of 2 with the leading coefficient of negative 3, so the easiest one might be something like negative 3x squared. A degree of 2 with the leading coefficient of 7, so maybe 7x squared, and with 2 terms, so I mean we can make any other term we want. All right. A degree of 1, leading coefficient of 1, so 1x. We can have as many terms as we want, but that's the simplest one. A degree of 0 would be any constant term like 7 or 11 or whatever we want. And degree 3 with a constant term of negative 8. So maybe we're going to say x cubed minus 8 might be the easiest one we could get. All right. If we look at the next page, in the next 3 lessons, we're going to investigate the characteristics of polynomial functions of degree 0, 1, 2, and 3. So let's look at degree 0 polynomial functions. The graph of the function f at x equals 3 is shown. All right, this line right here. It's got an arrow on each end, as all lines should have. State the domain and range of this function. So domain is all values right and left. So the domain is x is any real number. Our range is all values up and down. Well, this only has one value for y, and that is 3. Part B, write 2 other functions of degree 0 which can be graphed on the same grid. Well, we can say f at x equals anything we want, really, any whole number. So we'll say negative 5, and maybe f at x equals 1. So let's graph these. So f at x equals 1 would be right here. We'll change that color. F at x is 1. And let's do f at x is negative 5. That'll go through right here. Describe the general shape of each graph. Well, all these graphs are linear. State the number of y-intercepts of each graph. They all have one y-intercept. Do any of your graphs have an x-intercept? No. If so, state the function. If not, can you determine a polynomial function of degree 0 that does have an x-intercept? There's only one function of degree 0 that has an x-intercept, and that's f at x equals 0. All right. and that has an x-intercept that's infinite. All right, so this would have an infinite number of x-intercepts because it's right along the x-axis. So every single point on the x-axis is an x-intercept. Describe the relation between the equation of the function and the range of the function. Well, whatever the function equals, that's going to be your range. So if I said something like f of x equals k, then the range is y equals k. Part 2. Generalize from the above work to complete the following statements about all polynomial functions of degree 0 in the form f of x equals c. The graph is a line with a slope of 0. The domain is always x is any real number. This line goes forever right and left. The range is always equal to c in this form, f of x equals c. There are no x-intercepts except for the function f of x equals 0. When f of x equals 0, then this is the x-axis, and there's an infinite number of x-intercepts. And there's always one y-intercept, and that occurs at c if it's in this form. Part 3. Does the value of a polynomial function of degree 0 depend on the value of x? No, not at all. All right. Since the values of a polynomial function of degree 0 remain constant for all values of x, this type of function is called a constant function. Right? There is no variable in this function. F of x equals c. There's no variable. It's always going to be the same. All right, let's look at polynomial functions of degree 1. The graphs of 4 polynomial functions of degree 1 are shown. They have many characteristics in common. Make a list of the common characteristics in the space below. Well, they're all straight lines. They all have one x-intercept. They all have one y-intercept. Their domain is x is any real number, and their range is any real number. Y is any real number. So these graphs go forever right and left. Domain's any real number, forever up and down. Range any real number, that's why they've got arrows on them. How does a constant term in the polynomial function relate to one of the characteristics of the graph? Well, we learned from the last slide with degree 0s that the constant terms should be the y-intercept. And if we look at these equations, f of x is 3x plus 2, it goes to the y-axis at 2. 2x minus 4 goes to the y-axis at negative 4. Half x minus 4, the y-axis at negative 4. Constant term here is 0. It's got a y-intercept of 0. So the constant term is the y-intercept of the graph. Part C, how can you tell from the equation of the polynomial function whether the line increases from quadrant 3 to quadrant 1 or decreases from quadrant 2 to quadrant 4? So recall your quadrant numbers, quadrant 1, 2, 3, and 4. All right. So if I look at the coefficients in front, sorry, I guess you'll be able to see that. Both k at x and f at x increase from quadrant 3 to quadrant 1. Look at their coefficients, 3 and 2. How does that compare to the graphs of h at x and g at x, which both decrease from quadrant 2 to quadrant 4? They have coefficients of negative a half and negative a half. So we could say something like increase from quadrant 3 to quadrant 1 we've got a positive coefficient. That's a positive leading coefficient. And if it is decreasing from 2 to 4, that'd be these, it would have a negative leading coefficient. All right. Part D, the polynomial functions g at x and k at x are represented graphically by parallel lines. How can we tell from the equation of the function that this is the case? Again, if we look at the leading coefficients, they're the same. So in general, what feature of the graph is represented by the leading coefficient of a polynomial function of degree 1? Well, that feature of the graph would be the slope of the line. Part 2, generalize the above work to complete the following statements about all polynomial functions of degree 1 in the form f at x equals mx plus b. So the shape of the graph is linear with a slope of m. The domain is always x is any real number. These graphs always go forever right and left. The range is y is any real number because these graphs always go forever up and forever down. There is one x-intercept and one y-intercept, and the y-intercept is the b value in this equation. The direction of the line is determined by the value of the leading coefficient. If the leading coefficient is positive, the line slopes up from quadrant 3 to quadrant 1. If the leading coefficient is negative, the line slopes down from quadrant 2 to quadrant 4. Since the graph of a polynomial function of degree 1 is a straight line, this type of function is called a linear function. All right. Investigating polynomial functions of degree 2. Polynomial functions of degree 2 are called quadratic functions, and we studied these quite a bit in your grade 11 math course. The graphs of 4 polynomial functions of degree 2 are shown. So have a look at those. From the list of characteristics below, circle the ones which are the same for all the graphs. So if I look at all these graphs above, let's check the domains. So domain talks about going right and left. K at x goes forever right and forever left. F at x, forever right, forever left. G at x is forever right and forever left. And H at x is forever left and forever right. So all these things have the same domain, which looks to be x is any real number. The range for h at x and g at x is moving down, so the range is going down. Depending on what the vertex is, will determine our range. And the same thing for k at x and f at x, they're opening up. So depending on what those vertex points are, will change our range. The range is not the same in all of these. The number of x-intercepts. So let's see where all these graphs cross the x-axis. All right. K at x, it never does cross the x-axis. F at x crosses it twice. Looks like G at x down here crosses it twice. And H at x only crosses it once. So all the x-intercepts seem to be different between 0, 1, or 2. Check the number of y-intercepts. All right. K at x has one y-intercept. F at x has one y-intercept. Looks like G at x has a y-intercept right here, and H at x has a y-intercept right there. So looks like they all have one y-intercept, so the number of y-intercepts the same. All have one. How does the y-intercept of each graph relate to the equation of the quadratic function? Again, if we look at a few examples here, the y-intercept for k at x looks like it's 10. It's got the constant term of 10. For f at x, the constant term is -5. Let's have a look what the y-intercept is. You bet, -5. For g at x, the constant term is 10, and that one comes back down here, crosses y-axis at 10. For h at x, it's -8. Looks like it crosses here at -8 for h at x. So it looks like the y-intercept is still equal to the constant term. Even in degree 2 functions. All right. Part C. The graphs are all parabolas opening up or down. They all have one turning point with either a maximum or a minimum. How can you tell from the equation of the polynomial function whether the parabola opens up or opens down? Again, if we look at the leading coefficient, look at the leading coefficient. All right. If it's positive, the graph opens up. If it's negative, the graph opens down. How can you tell from the equation of the polynomial function whether their turning point is a maximum or a minimum? All right. Well, if the leading coefficient is positive, so if it opens up, then the graph has a minimum. Opens up, this point must be a minimum. And if the graph opens down, then the graph has a maximum. Right, if that graph's opening down, then that vertex point would be the maximum. The range can be written in the form y is less than or equal to a number or y is greater than or equal to a number. How can you tell from the equation of the polynomial function which form is appropriate? Well, again, if the graph's opening down, we'll start with up. If the graph opens up and we have a minimum, we've got a minimum, then our y values will all be greater than or equal to that minimum statement, that minimum value. All right. If the graph opens down, such as this one, and we have a maximum, then our y values will be less than or equal to that maximum number. All right. Y will be less than or equal to that maximum number. All right. So the max would give us a maximum number. The range would be less than that. If it opens up, the min would give us a minimum number, and all the values would be higher than that. So the graphs on the previous page show that polynomial function of degree 2 can have 0, 1, or 2 x-intercepts. The x-intercepts are the same as the zeros of the function. 3 of the functions on the previous page can be written in factored form, as shown below. Complete the following. The graph of f at x equals x squared minus 4x plus 5 factors as x plus 1 times x minus 5. This thing has, if you look at the graph on the page, it has 2 x-intercepts. Those x-intercepts are at -1 and +5. The graph of g at x, -2x squared plus 8x plus 10, can be factored as -2 times x plus 1 times x minus 5. It also has 2 x-intercepts. They're also at -1 and +5. The graph of h at x equals -2x squared plus 8x minus 8 can be factored as -2 times x minus 2 all squared. It has 1 x-intercept at +2. So example 1, consider the following polynomial function p at x equals 7 times x minus 1 times x plus 6, and the function q at x is negative of x plus 3 all squared. State the zeros of each function. All right, so for p at x, the zeros are here, we're going to have a 0 of positive 1, here we're going to have a 0 of negative 6. For q at x, the zeros are always negative 3. Part B, complete the table below with the characteristics of the graph of each function. So direction of opening for p at x, the leading coefficient is 7, so it's going to open up. Number of x-intercepts, we just found the zeros. There are 2 of those. There's 2 x-intercepts. The value or values of the x-intercepts, we found them to be 1 and negative 6. And to find the value of the y-intercept, we have to let x equal 0. So in our equation, 7 times x minus 1 times x plus 6, we let x equals 0, and we get 7 times negative 1 times positive 6, which is negative 42. So that's our y-intercept, negative 42. For q at x, the leading coefficient's negative 1, so it's going to open down. Number of x-intercepts it has is 1. That value is at negative 3. And again, to find the value of the y-intercept, we are going to let x equal 0. So the negative of 3 squared, which is negative 9. All right. Looking at the end behavior of a graph of a polynomial function. So the end behavior of the graph of a polynomial function describes the appearance of the graph at the left and at the right tail. For example, as the graph extends further and further to the left and further to the right. Degree 0 polynomial functions, we call these constant functions. The end behavior at each tail is to remain at its constant value as seen in figure A. So from left to right, the line extends from quadrant 2 to quadrant 1 or from quadrant 3 to quadrant 4. Or, if the function is f at x equals 0, then it's the x-axis. A degree 1 function, for the graphs of polynomial functions of degree 1, which we call linear, the end behavior is determined by the leading coefficient. So complete the following by inserting the word up or down in the blank space. If the leading coefficient is positive, as in figure B, that's positive leading coefficient, then the right tail of the graph will go up. Here's the right tail, goes up, and the left tail goes down. If we're talking about the leading coefficient being negative, as in figure C, then the right tail of this graph will go down, and the left tail of this graph will go up. For degree 2 polynomials, we call these quadratic functions. Again, the end behavior is determined by the leading coefficient, so complete the following by inserting the word up or down in each blank space. If the leading coefficient in a degree 2 quadratic function is positive, as in figure D, so my leading coefficient is positive, then the right tail of the graph goes up and the left tail of the graph goes up. Both tails go up. All right. If the leading coefficient is negative, as in figure B, then both tails go down. Example 2, complete the table using the word up or down to describe the end behavior of the graph of each function, and the word maximum or minimum or none to describe the nature of the turning point of each of the graphs. So f at x equals negative 2x plus 4. Well, because the leading coefficient is negative, the left tail should go up and the right tail should go down. And there is no turning point because it's a line. So this line would look something like this. Left tail up, right tail down. G at x, positive leading coefficient, and it's a degree 2 function. All right, so that means this parabola is going to open up. All right, so both the left tail and the right tail are pointing up. And nature of the turning point, well, because that's the lowest point on the graph, we call that a minimum. H at x, the variable has a degree of 1, so the leading coefficient is 3. That means it's positive. That means this graph should look like that. That means the left tail is going down and the right tail is going up. And because it's a line, there is no turning point. And for k at x, a degree 2 polynomial, so it's going to be a parabola. Leading coefficient is negative, so this parabola is going to open down. So that means both the left leg and the right tail, sorry, are both going down. And the turning point would be called a maximum. All right, you guys have your assignment. Way you go get after it.